I hope you're ready for the best dang AP Physics 2 prep in town because here it comes. And today we're talking about diffraction and interference, specifically in the context of light. Um, light, as you might know, is a wave. And diffraction and interference were one of the first things that we observed light do that really made us think it had to be a wave. Before that, when we knew that light could reflect and refract, we had it down. We thought it was a particle. Now we know the truth is a little more complex than either of those two options, but diffraction is sort of the thing that made us really think of light as a wave. And so to understand diffraction, um, we have to first introduce an idea called Huygens principle, which says that light emits a spherical wavefront. So there are pieces of light that as it is traveling forward will kind of emanate in all directions. If I have, a beam of light traveling like this, I can pick a little point on that light ray. And at this point, when the light was here, it's kind of spewing forth a wavefront that looks like that. It's coming out in all directions. Here it's only a 2D slice. It's coming at you out of the screen and all that as well. But light kind of is able to get around corners and edges by emitting in this way. So you could imagine if I had like a wall here, light shines over the wall, this little part of the wall could be illuminated by that diffraction. So normally, if the light's just going right over it, you would expect it to travel in a straight line and never come past. But light, it turns out, can get down in that region through this diffractive effect. What really gets interesting is how light behaves when it passes through thin slits or apertures. And so you could imagine if I take a flashlight and I shine it on a wall, what does the light do? Maybe it spreads out a little bit, but it puts a big old spot on the wall, right? Well, if I have a big opening in the wall, I take my flashlight again, and the light spreads, and some of it doesn't make it, but some of it does completely fill the hole in the wall there. If I've got a wall on the other side here, and I want to project that light on, we really just kind of get another spot. The light that gets through makes a spot on the wall, just as we expect. Maybe the spot's a little smaller because, the opening of this little piece here is smaller than just shining it directly on the wall, but we get a spot. That's not interesting. What is interesting is as we squeeze the size of that opening smaller and smaller and smaller, we shine our light here, only a little bit is going to go through. And so you might think, oh, we're just going to get a little tiny spot on the wall. But what we really get is, well, we do get a little tiny spot on the wall. But then we get a little band of darkness. And then another tiny spot above that. And then a little band of darkness below that. And so what we end up with is this pattern of alternating light and dark spots, which we really shouldn't happen if light does behave like a particle. If it just goes straight through the hole and shines onto the wall, we should expect to see the light doing that. But we shine light through a small opening, it's able to kind of bend around the edges and then spread out and create this very strange diffraction pattern. So when the opening is small, then a diffraction pattern forms. Well, why does that happen? Well, it happens because light is a wave, and really waves can interfere with other waves, or waves can interfere with themselves. Um, we kind of zoom in on our tiny little opening here. This slit is going to have a width that we're going to call A. So this is A. And it's small. It's maybe on the order of, tens or hundreds of micrometers. So we're looking at 10 to the minus 5, maybe 10 to the minus 4 at the biggest. But it's really tiny. You can barely see these with the naked eye. Um, and light comes through here. Light's going to shine on this wall. And we've already said that there's going to be bright and dark spots. So we get a bright spot here at the center, and then we get a smaller bright spot, symmetrical on either side of that. And then in between the central spot and these secondary spots are these dark areas. And that's interesting. We can imagine that light shining from the center of our slit here and light shining from the edges of one of our slit there each have to go to that dark spot in some sense. And so this one reaches the spot that way, and this one takes a different path to get there. And the idea is that since the lengths of these paths are different, we can kind of fit a different number of wavelengths along each of those paths. If we were to line up the wavelengths here, there would be a bunch of wavelengths on this path, a bunch of wavelengths on this path, and the way that they differ would be such that we get destructive interference. So the path length difference between the above paths results in destructive interference. In other words, those spots form because they are just the right distance from, say, the center of the slit and the edge of the slit, so that by the time the light that was here gets to the dark spot, and the time that the light at the edge gets to the dark spot, they are out of sync by exactly half a wave cycle. So we can write this destructive interference criterion as delta x is equal to sum m. M here is just an integer. Times lambda, the wavelength of the light, divided by 2. So we want path to differ by some integer multiple of half wavelengths. So they could be exactly 1 half wavelength out of sync. They could be 3 half wavelengths out of sync. They could be 5 half wavelengths out of sync. There's always 1 extra half wavelength there. M does have to be odd. If we let M be 2, for example, the 2 up top is going to cancel out the 2 down below, and we just get 1 wavelength out of sync, which would actually put them in sync. 1 wavelength shifted in length would get you back where you want to be. So whatever these paths are doing, we have such that this one has an extra half wavelength, whereas when this one, so this one might be, so that this way is on its way down when this way is on its way up. And so we have that these waves are out of sync by the time they line up. 180 degrees out of phase. So when does this happen? We can look at the limit where this screen we're projecting the pattern on is really, really, really far away compared to the size of our slit. So this is like tabletop experiment, half a meter long, normal everyday distances, whereas our slit is something like, again, 10 to the minus 5 meters. A is very, very tiny. Well, in that limit, if we're looking at the distance here, there is a difference in these lengths here, but if we were to zoom in on this portion here, and we look at how the light gets there, we can kind of roughly approximate in the region of the slit that this ray of light is parallel to this ray of light. So we're going to make the assumption they're not actually parallel, but at the end of the day, they're only differing by a fraction of a degree. Um, so we can roughly assume that they are parallel. It's a good approximation as long as the screen is far enough away. If we put it really, really close right up to the slit, we get near field diffraction, which is a whole can of worms we're not going to get into at all. But we're gonna take the easy way out here today. And so we're gonna pretend they're parallel. Just go with it. Because they're parallel, we can drop a line that is perpendicular to both of them here. And that means that beyond this line that we drop, these two rays are equal. They're always doing the same thing until they get to the screen. So the path difference then is just this little bit left over here. That's delta x, and that's what we ultimately want to solve for through this analysis. We're going to call this length here half the slit width, a over 2. And then if we do a little bit of geometry here, we can imagine a horizontal line coming from either of these points so that this angle we're going to call theta. And again, this would be if we go from the center of the slit and we kind of go until we hit that first dark spot we're looking for, this angle would be the angle from the center of the system to where that slit exists. So this is the angular position of the dark spot. Well, if we run it back, this horizontal dotted line here is perpendicular to the line formed by a over 2. So theta and whatever this angle is here must be complements. So that's 90 minus theta in there, which means that our angle theta again appears here. I drew this all very, very small, so let's blow it up a little bit and examine exactly what this is going to tell us. So again, vertical line, a over 2. We have a line representing a perpendicular line between our two light rays, which makes a right angle with this bottom line representing our path difference. This angle here is the same as the angle formed by allowing a horizontal line to go from the horizontal up to the light ray itself. So our light ray is here. Our goal is to find this path difference here. The geometry of this situation says that sine of theta is equal to opposite over the hypotenuse of the triangle. So we get delta x over a over 2. And that lets us say the path difference is equal to a over 2 sine of theta. If we employ our destructive interference criteria, that says we get to set this equal to m lambda over 2. The 2's on both sides of our equation. So really the reason that we chose to do like a over 2 instead of a is that the symmetry of the 2's match the the destructive interference criterion, and that lets the 2's cancel, and it ultimately lets us use any m instead of just the odd ones. So we make that cancellation, and we get the final equation, a sine theta equals m times lambda, rather. So this is angular location of the mth dark spot. If we want to find the first dark spot, we let m equal 1. If we want to find the second one from the center, we let m equals 2, and so on. So this is just, what number spot are you looking for? If we kind of rearrange this equation and get sine theta is m lambda over a, we can kind of see what's really happening here. For a given value of m, if I let the wavelength increase, wavelength's directly proportional to the left-hand side, and so that means sine theta also increases, which is equivalent to saying the pattern gets wider. we would find those dark spots further away from the center if we use larger wavelength light. So we can say the pattern widens with redder light. We think of longer wavelength light as being like the red light on the visible part of the spectrum. But if we were to somehow do diffraction with infrared, that would widen the pattern even more than if we did it with any kind of visible light. So longer wavelength is going to widen the pattern. This also says the size of the slit affects the spread here. So if A goes up, we have A is inversely proportional to the left-hand side. So if sine theta is going to go down, the pattern shrinks as slit grows. Or you can say as the slit shrinks, the pattern spreads out. The way I like to think about that is kind of like putting your thumb on the end of a hose. So if you have the light streaming through, making this smaller is going to have it spread out more, so to speak. I don't know if that picture was helpful at all, but you can kind of think of like smaller slit spreads more. You can think of this analogous as water flowing through a blocked nozzle. So that's single slit diffraction. We can kind of map this out. Again, this is a graph of intensity versus position. So intensity is how bright the light appears. Position. You can imagine a big, tall spike at the center. It's very wide, and then it goes up, and then down, and up, and down, and up. So these would be the smaller bright spots that appear to one side. It's going to be symmetric on the other side. And these minima here are going to represent the dark spots that the equation finds us. So this would be like m equals 1, our first one on either side. M equals 2 is the second one, and so on. So these are our dark spots. Sometimes the angle is an impractical thing to measure. And so instead what you would want to do is once you get this pattern, so if this is how the pattern looks in intensity, what it would actually look like on the screen would be like a big spot there and then smaller spots coming out. Instead of measuring the angle, what you might actually want to do is measure from the center of the system the distance at which the center of the dark spot appears. So you look at this feature like delta y, the actual distance on the screen where dark spot is located. This is something you can actually get in and practically measure with a small, very accurate ruler. The way that you can do this is by employing the small angle approximation. Which is based on the idea that if I have a sine function from 0 to 90 degrees, it looks kind of like that, half of a hump. Well, when theta is small, you can kind of squint a little bit and you can think that this looks approximately linear. So I can say that sine of theta is approximately just equal to the theta, if that is small enough. You can also show this more directly if you know the dark arts of the Taylor expansion. But, AP2, we're not expected to know anything about that. Tangent also behaves this way when the angle is small. So if we're in this regime, sine is approximately equal to tangent, which means that if we are working with small enough angles, and if, again, our whole assumption was that A was much, much smaller than the distance to the screen, if that is true, then this distance y L is the distance to the screen, theta is the angle at which it appears from the center of the slit, then by trigonometry, tangent is opposite over adjacent. So we get delta y over L. But we get to cheat here and say, well, sine is also opposite over adjacent. Wink, wink. That lets us go back to our equation, a sine theta equals m lambda, and replace the sine theta with the ratio of the position of the spot over the length, the distance from the slit to the screen. So we can replace that and say now that y is equal to m lambda times L over A. So this is a way to allow us to measure the actual distance the spot appears rather than the angle, which could be pretty tricky to measure in a practical way. So that's the magic of the small angle approximation. This works in most cases for the first couple of m's. As m gets larger and larger, the pattern gets wider. And so the fact that this angle is small enough to give you that will probably start breaking down after, like m equals 7 or something like that. So if you're looking for m equals 30, you probably can't use the small angle approximation. You may have to use the actual formula. But that's the price you pay. Now that we've finished single slit diffraction, we can look at two slit interference. Instead of a single slit, now we have two slits. Each of these is still going to have a width A, but now we're going to measure from the center of one slit to the center of the other a distance D. So D is going to represent the slit separation. If we shine our laser or our light on this system, we get a different kind of pattern. If you draw an intensity plot again, what you observe is you still kind of get the same overall diffraction pattern, but inside of that diffraction pattern is a much more fine structured series of bands or fringes. So you get this really bright, thin peak at the center, and then you get these smaller little fingers inside of the overall diffraction pattern. So these solid lines represent the actual stripes, but they seem to be kind of constrained by what the earlier diffraction pattern looked like. And it should be symmetric on both sides, even though I'm not artistically drawing it that way. So if you kind of zoom in, and what you would look at the screen is you would see these kind of blobs, but they're kind of subdivided into finer structures where each of these smaller peaks are. This next blob would be like the first bright diffraction spot, but there would be these, again, finer structures there. These are roughly all the same brightness within each spot. It's just that you will see an overall very large dark spot from diffraction with these interference finer structure inside. So we have an overall diffraction pattern with finer interference pattern within. It's worth noting that the diffraction is controlled by the slit size. The interference, so diffraction, dotted line, interference is the solid line. It's controlled by D, the slit separation. So it's possible to like substitute out this system with a similar one with the same separation but different a values, and you would find these finer features to be in the same places, but the locations of the dotted line pattern would change. So you should be careful when reading problems. You really have to parse them to see, am I looking for, I have a two slit system, am I looking for the diffraction minimum, in which case I care about what the slit size is doing, or am I caring about the interference maximums, where I care about what D is doing? It's really the same equation to model two-slit diffraction or two-slit interference as the previous one, but we're doing D sine theta equals M lambda. This equation uses the slit separation. And this is specifically looking for the bright interference lines. The equation we had earlier for the diffraction scenario was for the dark diffraction minima. This is looking for the bright interference line. So the context is a little bit different, but the same exact structure is here. We have some length that's privy to our system, whether it's the separation or the slit size itself. We have the sine of the angle being what angle you will find that feature at, equals m, just a number, 1, 2, 3, 4, 5, so on, times the wavelength. This comes from looking at how the light interferes. We're still looking at a path difference from one slit to the other. We're still building a triangle, looking at the path difference. If these are roughly parallel, then the path difference is the bottom here. So now we have D there as the hypotenuse of our triangle, delta x, and sine theta. We set delta x equal to the constructive interference criterion, where they just differ by a single integer value. Integer value of wavelength gives constructive interference. And then we solve this triangle. Delta x is equal to d sine theta. And that's where this comes from. Last but not least, I know we just did 2 and you're itching to see 3, but we're going to skip to like 10,000 slits and see what happens there. And when you do that, you build what's called a diffraction grating. These are usually simple little films. Usually can't see the slits by the naked eye, but like in this little film, you have etched into it thousands and thousands and thousands of slits. I'm not going to draw them all, but there you go. And you might have this rated by something like, it'll say, 13,000 slits per inch or something like that. So you're given a number of slits per inch. What this does is, because there are so many slits, there are so many more opportunities for interference to occur. And what you have now is, if we're looking at the intensity plot again, you have some very bright, pronounced spots, and that's about it. Make it smaller as they go along. So this would be like m equals 0, m equals 1 would be symmetric on both sides, and m equals 2 would be the next one out. So we get very bright, distinctly spaced spots. The equation is literally the same as what we just saw. We're going to get m lambda equal d sine theta, where this is the distance between adjacent slits. Or oftentimes you will see this written as m lambda equals 1 over n sine theta. And n here is the number of slits per unit length. So if we were looking in inches, we would put 13,000 there for n. There are 13,000 slits per inch, which would give us 1 over that large number, which would make d a very small number. So you can either look at the actual slit spacing d, or you can write this in terms of 1 over that value, the number of slits per inch, which is usually what you'll be given if you work with one of these practically. Diffraction gratings are really cool for use in things like astronomy because of how strongly these peaks are spaced out. If you have light that is from more than one wavelength, so maybe you're observing a nebula and you want to know what that nebula is made of, you can look at multicolored light and you pass it through a grating, and it's going to clearly separate out the colors. Because each kind of molecule has its own kind of distinct signature of light that it produces, you can look at that, put it through a grating, and see, oh, I see a big yellow spot, and that might be sodium, and I see a big red spot, and that might be hydrogen or something like that. So this is really useful in astronomy or chemistry, where you have a sample. You can look at all the kinds of light made by that sample, and then you can identify what it really is by looking for certain signatures within that. So that's a really useful technique used in a lot of different scientific fields, actually. All right, we looked at interference in 1, 2, and many slits, and so that should get you through. Note again, we introduced 3 different equations. They're all really the same. There's some m lambda equals some length times sine theta. You do have to be a little bit careful. For one slit, you're looking at dark spots. For 2 slits or many, you're looking at the bright spots. Here, the bright spots, we're saying they come from interference, which is based off slit separation. The dark spot is based off diffraction, which is based off slit size. So really, really read a diffraction problem carefully. Are you looking for dark spots? That's going to usually be controlled by the slit size and diffraction. Are you looking for bright spots? That's going to be controlled by interference and the slit separation. So by carefully looking for those words, you understand the context of what you're looking for, and you won't get it mixed up when they definitely try to trick you on those multiple choice questions. All right, that's all for this one.